Hello, everyone. Welcome back. Today, we're going to go over section 4.2, just talking about the second derivative test. In section 4.1, you learned how to find the intervals where a function is concave up or down. And in that section, 4.1, you also learned how to find inflection points of the original function. Well, section 4.2, we're still going to be talking about concavity. But instead of finding intervals where your function is concave up or down, you're going to be using concavity and making connections to how concavity relates to local extrema, something that we've actually seen before. So let's take a walk down memory lane. First, for some context, remember, or you might recall from section 3.5, we talked about the first derivative test. And in the first derivative test, your conclusion was where any local extrema were. And the way we did that is by using a number line analysis, putting critical numbers on a number line, and then we picked test points in the region and plugged those into the derivative. If you know where your function's increasing and decreasing, you can determine what happens at those critical numbers. This was section 3.5, and this was the first derivative test. You used interval testing on the first derivative to figure out where any local extrema are. The second derivative test, which is what we're going to do today, is again a test to figure out where any local extrema are. So I do want to make a note that both the first derivative test and the second derivative test find local extrema. We just do it different ways. So this is where we're going to find our local maxes and mins. This is a very important thing to note. We have a whole lot of tests. We have a whole lot of processes that we're learning how to do. The first derivative test from section 3.5, we did a number line analysis using the first derivative. The second derivative test, which we're going to do today, is a different process, but in the end, these two tests have in common that you're finding where the local maxes and mins are. It's just one way you're doing a number line analysis, and the other way, well, we're going to find out. So I just wanted to give you guys some context here that both of these are testing the same thing, finding local extrema. So then how do we do that? Well, let's take a moment to think about what local extrema look like. If I love drawing my generic cubic here. If we have such a curve, then we know we can identify our turning points on the graph. I have a turning point here, and I have a turning point here. This turning point we would have called a local maximum. And this turning point we call a local minimum. But if you take a look at a local max, and you think about the characteristics of your curve, one, you see that at local maximums, your function's increasing on one side and decreasing on the other. That's a fact that we used for the first derivative test. But if we look at the shape of my curve over this entire region here, local maximums correspond to my graph having to be concave down. So we learned in section 4.1 how to tell when a function is concave up or down. Well, as it happens, a function has to be concave down if there's going to be a maximum. I challenge you to find a maximum point that doesn't have concave down shape. You ain't going to find one. But if we look at a local minimum, what has to happen? The local min has to be in the bottom of a bowl. And that bowl has to be upright. So it has to be concave up at a local min. So think about if you have a bowl or any kind of dip in your curve, If you drop a ball in it, say, pretend this is a bowl, the ball is going to bounce around in here, but it's eventually going to settle kind of in the bottom of the bowl. This bottom is your local min, and the reason why it collected down there was because this thing is concave up. It's got that upward shape. It's an upright bowl. On the other hand, think about inverting this. If I have my bowl upside down, the very tippy top, my local maximum, but it has to be that the bowl is upside down. So we have the concave down curvature there. So this is to say that on a graph, if I know where the local max and mins are already, you can kind of reason to yourself, okay, it has to be concave down at a local max and concave up wherever there's a local min. You can also use that process in reverse. If we don't know where the local mins are, like we're flying blind, we don't know what my graph looks like, then what you can find are the potential maxes and mins, our critical numbers from section 3.5. If you know where your potential maxes and mins are, your critical numbers, you can test the concaveness of your curve there and then determine whether or not it has to be a max or a min. So if we don't know what the maximums or minimums are, we can't see them, you have this reverse process. Find the potential maxes and mins, and then you can find whether or not my function's concave down or up. If you know your function's concave down, then that potential max or min has to correspond with a max. If you know your function's concave up, then that potential max or min has to correspond to a local min. That's the thought process behind the second derivative test, which is right here. It says, if f double prime of c, and we're taking this c to be a critical number, if you found your critical numbers, if you found your critical numbers and you've plugged it into the second derivative, if your second derivative is negative, or that is less than 0, that means your graph is concave down, and that's where a local maximum is going to occur. It says, if f double prime of c is defined at a local maximum, then the curve must be concave down. If f double prime of c is defined at a local minimum, then the curve must be concave up, or that is to say that the second derivative must be positive. The second derivative must correspond to concave upness. Remember, second derivative, its whole purpose for existing is defining concavity for me. And now I'm going to use that second derivative to tell me, to kind of tattle on the original function, f. Where's its maxes and mins based off of what I can tell about the concavity? That's a neat little trick. So let's put this to use. Let me show you the steps here. The second derivative test, which we have labeled here, these are the steps for it, here in number 3. The first sentence or so is a lot of qualifying information. Suppose that f is a function and that you can find the first and second derivative on an interval. And let's say that you have your critical numbers. Then if you take that critical number and plug it in to the second derivative, if you get a positive result for that, then it must be that my graph is concave up. Positive value for the second derivative means concave upness, and therefore that critical number must correspond to a local minimum. If you take your critical number and plug it into the second derivative and you get a negative result, then that means that your graph is concave down there, which means that that critical number has to correspond to a local maximum. This gives you the process, how you're going to figure out where the local maxes and mins are. First, you have to find your critical numbers, your potential maxes and mins, but instead of putting them on a number line and testing points using the first derivative, we're going to instead take those critical numbers and plug them into the second derivative and let the second derivative kind of tattle about what the shape of my curve is. And if I can tell the shape, I can tell whether or not they're a max or a min. On the other hand, sometimes you can take your critical number, plug it into the second derivative, and then you get it's equal to 0. So it's neither positive or negative. So if that ever happens, if you take a critical number and plug it into the second derivative and you get a 0, then what we'd say is the test is inconclusive. It fails to give me any information about it. So that is to say, we don't know what would happen there. We'll show when that comes up. Alrighty, let's practice this idea. Suppose that we have a function, f of x is 4x cubed plus 12x squared minus 180x. And I want to find any critical numbers of the function. So that means critical numbers come from, we have to remember this from section 3.5, critical numbers come from taking the derivative, the first derivative, and setting that equal to 0. Critical numbers, if you might recall, also come from values that make your derivative undefined. But the nice thing that comes as a consequence is that when you take the derivative and you're looking for potential maxes and mins, the only time you'll have a max or min comes from the nice case where you set the derivative equal to 0. So that is to say that when I'm looking for critical numbers today, I'm going to be looking for where is the first derivative equal to 0. And we won't have to worry so much about where the derivative is undefined. Let's take the derivative of this thing. We got the derivative of f is 12x squared plus 24x minus 180. And then I'm supposed to be setting that equal to 0 and solving for x. So I want to look at how to factor that, because factoring is usually your friend when trying to solve these things for x. What I'm going to do is I'm going to pull out a 12 from each of those terms. You have 12 times x squared plus 2x. Now 180 divided by 12 is 15, so that becomes minus 15. And I'm setting that equal to 0. Let me double check the 180 divided by 12 thing. Yep, it's 15. Okay, let's factor this thing. We have negative 15 here. I want things to add up to 2, so I want to factor that into x plus 5 times x minus 3. I'm going to set this equal to 0. Now, whenever we have a multiplication equal to 0, it's only equal to 0 if each of the parts are. So I'm going to set x plus 5 equal to 0 and x minus 3 equal to 0. Add the 3 over, subtract the 5 over, and we have our two critical numbers. I have negative 5 and 3. Now, this is where we're going to deviate from what we had done in section 3.5. At this point, when we did the first derivative test, we would have did a number line and put these values on a number line. The second derivative test is different because we are doing 0 number lines today. No number lines. Instead, what you're going to do is you're going to say, okay, these are critical numbers. These are my potential maxes and mins. So much potential. We got to figure out whether or not they correspond to a max or min or neither. And what we're going to do, instead of putting them on a number line, is plug them into the second derivative. So our next step in this long process, well, it's not too long actually, is to take the second derivative. I'm going to need it. Here's my first derivative. Take the derivative of this line, term by term, to get the second derivative. The derivative of 12x squared is 24x. Derivative of 24x is 24. And the derivative of 180 is 0. So this is my second derivative. And remember, the second derivative, its whole thing, its whole purpose for existing is to tell me where my function's concave up or down. So what I'm going to do is I'm going to use this concave up or down function right here to tattle on what is the concavity going on at these 2 points. So what you do is you plug the critical numbers right on in to that second derivative. So I'm going to find f double prime of negative 5 and f double prime of 3. Now this is where I'm going to punch this in my calculator here and see what I get. So I have f is 24x plus 24, or sorry, f double prime is, that's my second derivative function. And I want to plug negative 5 and 3 into the second derivative. So when I do that, I get negative 96 out and positive 96 out. Now, I don't really care so much about what the value is, but I care that this is now negative. And remember, the second derivative does what? It tells me concavity. So if I get a negative result from the second derivative, this thing's telling me that my function is concave down at this critical number. Since it's a critical number, and it's potentially a max or a min, and it's telling me that it's concave down at that potential max or min, what's it going to be? The only shape that's possible indicates that it has to correspond to a max. And so what you would say there at this point is that there is a local max at x equal negative 5. So I kind of started the next steps work. If you relocate this down here, this is kind of where it's appropriately asking this thing. Part B said find the second derivative, and we go here, go. Use the second derivative test to locate any local max and mins. That's what we're doing here. We're taking our critical numbers and plugging them into this. So similarly, if I plugged in my 3 critical number, I get a positive result from the second derivative. This is telling me that my function is concave up at that critical number of 3. If it's concave up at a critical number, and that critical number is going to be a max or a min maybe, then it's got to be a local min right there, because the concave upness would not allow for it to be the other shape, a maximum. So what we should say here, what we should conclude, is that there is a local maximum at x equal negative 5, this critical number, and that there is a local minimum at x equal 3. Let's go ahead and find the points associated with that, an xy coordinate point that we can plot. So if we have a maximum at negative 5, I want to find the corresponding y value for that, so I can plot it on a graph. So let's find the point corresponding to 3 as well, 3 comma y. I'm going to take and plug these two values into the original function. Remember, y values you get by plugging things into the original function. That's what the original function does. So if we go back to the first page, you'd see that the original function was 4x cubed plus 12x squared minus 180x. So when you punch in your x value of negative 5, we get a y value of 700. When you punch in your x value of 3, we get a y value of negative 324. So what we would say here is that the local maximum occurs at negative 5, and the local maximum is 700. Similarly, we would say that the local minimum occurs at 3, and the local minimum is negative 324. So this process is kind of neat. You find your critical numbers, which come from the first derivative, setting that equal to 0. You would then take those critical numbers and plug them into the second derivative. And all you're doing is using that second derivative to kind of tattle on what the shape of the curve is right there at that critical number. So if you have the shape of your curve is concave down at that critical number, then it has to be a maximum there. If you have the shape of your curve is concave up at that critical number, it's got to correspond to a local min. We're going to get lots of practice on this today. Let's scooch on down here to number 2. So suppose that f double prime is 3x squared plus 6x minus 4. Now this means that they're giving you the second derivative, right? They gave you f double prime. They're not giving me the original function here. They gave me the second derivative function. So let's read the rest of it. It says, use the second derivative test, this thing up here that we just did, to determine what happens at these critical numbers below. And then it says, assume that f and f prime are continuous functions. This just means that we're going to assume that there's no domain restrictions and no hiccups and bumps in no hiccups or gaps or anything weird going on with my functions. Like, everything's going to play nice, in other words. If this is my second derivative, and they're giving me critical numbers down here. They want me to test them. That's what it says. These critical numbers come from the first derivative, but if they're given the title critical number, that means they have this shiny possibility of maybe being a local max or min. As soon as a number has that title, it's a critical number. That means, whoo, maybe it's a max or a min. And what they gave me was the second derivative. So it's not like I can do anything with the first derivative because they didn't give it to me. They didn't even give me the original function. So I'm stuck with doing the second derivative test, which says take those critical numbers and plug them in to the second derivative. So let's do it. We have f double prime of 1 here. 3 times 1 squared plus 6 times 1 minus 24. So we have 3 plus 6 is 9 minus 24. So that looks like a negative number to me. So we should draw some conclusions from this. If I get a negative number from the second derivative, what does that mean about the shape of the curve? If I have a negative number from the second derivative, that implies that my function is concave down. Remember, all we're doing is using the second derivative to tell me the shape. So if I get a negative number, we say it's concave down, and therefore the second derivative has served its purpose. It's told me that the graph is concave down. It's up to us to put 2 and 2 together. What does that mean about my function? Well, we plugged in a critical number, and my graph is concave down. So if you draw your little shape, your bowl shape, it's concave down, what has to happen at that critical number? It has to be a maximum because that's how the shape of the curve looks. So what we should conclude here, to kind of summarize it, is that there is a local maximum at x equal 1. Since we don't have the original function, they did not give it to us, I cannot find the y value that corresponds to x. So all I can say is that there is a local max at the x value. I don't actually know what the y value is. And never mind these 3 dots. This is just my little way of, putting the answer right next to this. So these 3 little dots just mean therefore. You don't have to write those. It's just a habit of mine. This is where I will write 3 little dots and then write my conclusion next to it. It's just a way to draw my eyes to where I wrote my answer. Okay, next up. They're telling me x equal 4 is a critical number. And I'm going to do the same thing I just did. I'm going to plug that thing into my second derivative and see what happens. I'm going to use that second derivative there to tattle about the shape of my curve going on at 4. Now, when you punch this out, we get a value of 48, which is a positive result for the second derivative. So if we just draw the natural conclusion there, positive result from second derivative means your graph is concave up. So we have to put 2 and 2 together. If this is a critical number and it's maybe a max or a min, and it's concave up there, what does that tell me about my critical number? It has to correspond to a local minimum. So what we would say here is there's a local min at x equal 4. And that's it. Since I don't have the original function, I can't find the y value. This is all we can say. There's local min somewhere along x equal 4. Right, let's do this one more time. We have C, x equals 2. They're saying this is another critical number that they found. And I'm going to plug this critical number into the second derivative. F double prime of 2 would be 3 times 2 squared plus 6 times 2 minus 24. So we have 3 times 4, which is 12, plus 12 minus 24. This gives me 0. So we plugged a critical number into the second derivative, and I got 0. This is neither positive nor negative, so I can't draw any conclusions about the shape of my curve there. What we should say then about this test is the second derivative test has been inconclusive. Is inconclusive at x equal 2. So if you take your critical number, plug it into the second derivative, and you get 0, this is a big we don't know. Like, we can't say one way or the other whether 2 corresponds to a max, a min, or anything. So I would have to do the first derivative test, my number line analysis on this, to actually draw a conclusion about 2. So we would say that we don't know what happens at 2. Can't say for certain one way or the other. Well, that's a statement, not a question. Leave that there. We don't know what happens at x equal 2. Alrighty, let's move on to number 3. Now this is where they're kind of shoving us all the way in. So far, they were giving us questions where they had it broken up into little steps, and we had to put little pieces together one bit at a time. Number 3 is where we start doing all of it in one go. They're going to give us a function, and we're going to take that function and have to find any potential maxes and mins, find the critical numbers, and then they want us to use the second derivative test, what we've just been doing, to determine whether those critical numbers correspond to any maxes and mins. All right, let's get started. If we have x to the 4th minus 32x squared minus 10, and it wants me to find any local maxes and mins, the first thing you need, regardless of how you're doing it, is to find any critical numbers. That's always step 1. So let's take the derivative of my function. Critical numbers always come from the first derivative. Always come from setting the first derivative equal to 0. First derivative. So don't forget that part. That's what we're doing. Where you take the first derivative, we find it, and then we're going to set it equal to 0 to get my critical numbers. So let's take our first derivative. We're going to have 4x cubed minus 64x. The derivative of minus 10 is 0. I'm then supposed to take this derivative function and set it equal to 0 and solve. Usually, well, in this case, factoring is definitely going to be your friend here. Let's take one of these x's and pull it out. Actually, we can take a greatest common factor out of both of these terms. It looks like I have 4 goes into 4 and 64, and x will go evenly into those as well. So I'm going to pull out a 4x. Now, when you have 4x cubed divided by 4x, you get x squareds left, and 64x divided by 4x is 16. I'm trying to solve that set equal to 0. And when you have something like this set equal to 0, this is now factored in a way. This is one term times another. And the only thing that lets these two things multiply to be 0 is if they both are set equal to 0 off the side. So what we do is we set both of these equal to 0 and solve those separately. If you have 4x equal to 0, you divide both sides by 4, you have x equals 0. If you solve this one, you add over the 16, you have x squared is equal to 16, square root both sides, don't forget your plus or minus. We would have plus or minus the square root of 16, which is plus or minus 4. So I have 3 critical numbers here. I have x equals 0, I have x equal 4, and I have x equal -4. These are my critical numbers, which means they are my candidates for being maxes and mins. There won't be any others. This is it. If there's going to be a local max or min, it's going to happen here, here, or here. So we have to figure it out. But this is where, instead of doing a number line analysis like we did before, This is where the second derivative test comes in, and instead we're going to take these and plug in to the second derivative. That's how the second derivative test works. You take your critical numbers and you plug them into the second derivative. You're going to use the second derivative to kind of tattle on what the shape of the curve is there. So that means if I'm going to plug them into the second derivative, I need to find the second derivative. So come all the way up here, where you just took your first derivative, and take the derivative again. You end up with 12x squared minus 64. Take those critical numbers right there, all three of them. Plug them in to the second derivative so that you can figure out whether your function is concave up or concave down at these critical numbers. So let's put this in our calculator. Put the second derivative in there, 12x squared minus 64. You wanted to plug these into the second derivative. So plug in 0, we get minus 64. Plug in 4, and we get 128. Plug in negative 4, and we get 128. So we have to draw some conclusions then. If we have a negative result by plugging in 0, and this is a negative result for the second derivative, that is telling you that your function is concave down. That's all it tells me. Negative value for second derivative means concave down. But we're supposed to put 2 and 2 together here. This is not just any number. This is a critical number. This is a potential max or a min. It's a special fella. But if I have it's a special guy, and my function has to be concave down, this upside down bowl shape, which is this special guy going to be? Is it going to be a max or a min? It's got to correspond to a max. Similarly, if we move down to the next one, I plugged in 4, and I get a positive result for the second derivative. That means your function is concave up right there at 4. And it's up to us to put 2 and 2 together. If our function's concave up and it has this upright shape, but 4 is a critical number, and it has this special quality of maybe being a max or a min, which would it have to be? Concave up, max or min, got to correspond to a min. So we have a max going on there, a min going on there, and by the same logic, the same thing would happen at negative 4. F is concave up. It has this upright shape, which means that critical number has to correspond to a minimum. All right, let's write down our conclusions, and we're going to find these as points. I have 2 local minimums. At one is going to be at 4 with its corresponding y value. And then I have a second point going on at negative 4. And I'm going to write its corresponding y value as well. I have 1 local maximum going on at 0. And we're going to find its corresponding y value. These are points, right? These are points that you can plot on your graph. X, Y, X, Y, X, Y. So if I want to find a point, I've got to take all 3 of those numbers and plug them back into my original function up here. That's what the original function does. It cranks out y values. So let's put it in my calculator now. X to the 4 minus 32x squared minus 10. We've got 4, plug in 4. I get a y value of negative 266. Plug in negative 4, and I get a value of negative 266. Plug in 0, I get a y value of negative 10. So I have 2 different local minimums that are spaced a little bit apart, but I've got a local minimum at 4 that dips down to negative 266, and then also it happens at negative 4. It dips down to negative 266. I have a local maximum spot here at 0, negative 10. So we'd say the local maximum is negative 10. All right, there's my conclusions by that one. We're doing this using the second derivative test. Remember, second derivative test, critical numbers plug into second derivative. Critical numbers go into the second derivative. Let's do this one more time. It's still asking about local maxes and mins, and they're wanting us to do it using the second derivative test. So that means firstly, you need to find your critical numbers. What are my candidates for being the maxes and mins? So let's take the derivative, f prime of x. We get negative 6x squared minus 24x minus 18. Take the derivative of that fellow. And to get critical numbers, what do? We take that, and we're going to set it equal to 0 and solve for x. Again, factoring is your friend with this type of thing. So if I'm looking at this equal to 0, I'm going to take out a minus 6 from this as a greatest common factor. So negative 24 divided by negative 6 is positive 4. So I have positive 4x. Then I have negative 18 divided by negative 6 is positive 3. There we go. Now let's factor this quadratic here in the middle. It factors into x plus 3 times x plus 1. So when you set each of these pieces equal to 0 and solve, you'll have your critical numbers. Now before, I think on the last one, I'd had this term and I'd set it equal to 0. This is just a constant here. It doesn't have an x, so it's not like you can set negative 6 equal to 0. Right? If this was an x hanging out here, negative 6x, then you could set that equal to 0. But this is a constant, so, I mean, it's never 0, so you can't set it equal to 0. We ignore it, in other words. The only thing that's going to get set equal to 0 here is this and that. Subtract the 3, subtract the 1, and we get two critical numbers. That shiny title that means these are possibly maxes and mins. We've got to figure it out. But instead of putting these on a number line and doing interval testing, we are doing the second derivative test, which means you've got to plug these into the second derivative. That means that we need the second derivative now. So while we're here, let's do this. Let's find the second derivative. So we go back up here where I found the first derivative, and we take the derivative of that term by term. Get minus 12x minus 24. I'm going to take these two critical numbers and chuck them in here and see what this is telling me is going on at my critical numbers. So if you plug in negative 3 into this, you get negative 12 times negative 3 minus 24, which is 36 minus 24, which is 12. When you plug negative 1 into that, you get 12 minus 24, which is negative 12. Now it's up to us to make conclusions out of this. I plugged a number into the second derivative, and what that tells me is I get a positive result here, which tells me that my function is concave up. So second derivative tells me concavity. Positive value from second derivative means concave up. Now it's up to us to draw even further conclusions. Negative 3 was a critical number, which means it's potentially a max or a min. And if my function is concave up there, that means that it has to be a min. It has that upward shape. It must be a minimum. I plug in negative 1, that other critical number, and I get a negative value, which means that f is concave down there. So if it's concave down, what does that tell me is going on at that critical number? It must correspond to a local max. So I have a min going on up there and a max down here. Let's write our conclusions. I'm out of space down here, so I'm going to do this over in this corner. I have one local minimum, and it occurs at that critical number, negative 3. So we're going to find the y value that corresponds to negative 3. Make it a point that you can plot, x, y. And then I have a local maximum from over here happening at negative 1. Let's find these points. I'm going to plug these two x values into the original function here. Oop, I just put the derivative function in there. We want to plug this into the original. The original function gives me y values, so be careful on that. Negative 2x cubed minus 12x squared minus 18x. We're plugging these into the original function so that I can get y values out. Be careful. Go back to our table. Delete some of our old stuff. Plug in negative 3, we get a y value of 0. Plug in negative 1, and we get a y value of 8. So these are my points that you can plot. We'd say there's a local maximum at negative 1, and the local maximum is 8. There's a local min at negative 3, and the local min is 0. All right, let's do this one. Same thing, find the local maxes and mins using the second derivative test. So the very first thing you need to do is find your critical numbers. I need my candidates. We're going to take the first derivative. Now, since this is something in parentheses to a power, what we're going to need to take the derivative here is the general power rule. So let's do it. We got 1 times 2 is 2. Leave the inside alone. Decrease the power by 1, and then multiply by the derivative of the inside function. The derivative of x squared minus 25 is 2x. So I'm going to clean this up just a tad, because we're going to do algebra with it, right? Let's take this 2x and scoot it to the front. This is 2 times 2x times x squared minus 25. Which, if you multiply the 2 times the 2x, that's 4x. Now, what am I supposed to do to find critical numbers? You take your derivative and you set it equal to 0 so you can solve. So thinking ahead, it would actually be counterproductive to take this 4x and multiply it in. This is actually kind of pre-factored in a way. It's this times that. So that is to say, don't multiply this other term through. It's actually already in a good spot for you. If you have this equal to 0, the only thing that makes something that's multiplied equal to 0 is if the separate parts are. So we split this up, and we take each of these pieces and we set those equal to 0. Solve those. 4, or if I divide by 4 on both sides, I get x equals 0 over here. If I add the 25 to the other side and square root it, I get x is plus or minus 5 over here. I have 3 critical numbers. X equals 0, x equals 5, and x equals negative 5. Now, because these are critical numbers, they are potentially maxes and mins. And in order to figure out if they are maxes and mins, you're going to take those this time and plug them into the second derivative. That's called the second derivative test. So just remember, when you plug critical numbers into the second derivative, that's called the second derivative test. That's what we're doing all this time. So if I'm going to plug these critical numbers into the second derivative, the next thing you need then is the second derivative, because we haven't found it yet. So I want to take the derivative of f prime. Now, I mentioned here that it was advantageous to leave this factored because then you can pull off your critical numbers. But now I'm getting ready to do the derivative again, and I would really like to get away from having to use a product rule, because this is one function times another. So if I'm going to take the derivative of this, it actually it's in our interest now to go ahead and multiply that in, just so I can get away with not doing a product rule. 4x times x squared is 4x cubed, and 4x times minus 25 is minus 100x. So I wanted to take the derivative of this, but I don't want to have to use a product rule, so I'm multiplying it in down here, so that now my derivative, my first derivative, just looks like a polynomial. I'm simplifying it down a little bit here. Now let's find the second derivative, f double prime. Derivative of 4x cubed is 12x squared. Derivative of minus 100x is minus 100. There's my second derivative. I'm going to take each of these critical numbers right here and plug them into this and draw some conclusions. F double prime of 0, f double prime of 5, and f double prime of negative 5. I'm going to make the second derivative tattle on what the shape of my curve is at those critical numbers. Let's put in our derivative, 12x squared minus 100, and punch in these critical numbers. I plug in 0, I get the second derivative value of negative 100. Plug in 5, second derivative value of 200. Plug in negative 5, second derivative value of 200. Negative result from the second derivative. That means my graph is concave down, right there at 0. So if it's concave down at this critical number, that means that critical number has to correspond to a max. When I plugged in 5, I got a positive result from the second derivative. That means my graph is concave up. If my graph is concave up, that means that critical number has to correspond to a min, just because that's what the shape of the graph requires. You can't be concave up and not have a min. If I have the same thing happen here, positive result, it's concave up at negative 5, that means that there's got to be another minimum at negative 5. So let's write our conclusions and write them as a point. I have two local minimums. Local minimums at, one's going to be at positive 5 with its corresponding y value, and one's going to be at negative 5 with its corresponding y value. We'll find those here in a minute. And then I have one local maximum. And it occurs at that 0 critical number. All right, let's plug those values back into the original function up here, this one, so I can get the corresponding y values of those maxes and mins. X squared minus 25 squared, that's my original function. So I'm going to come and punch in 5 to get a y value of 0, negative 5 to get a y value of 0, and plug in x equals 0 to get a y value of 625. So I have two local minimums at 5, 0, and negative 5, 0. I have a local maximum at 0, 625. All right. This is the gist of it. You use your first derivative to find your critical numbers, and to use the second derivative, that means you take your critical numbers and you plug them into the second derivative to tell you the shape of your curve. Once you know the shape, you can decide whether or not they're maxes and mins, and then you can write them out as points. We're not quite done with this section, so please join me in the next video when we finish up this section.